So today we are going to do first order questions. Huh? All right. So now we are going to do the first order question or first order reactions. When we are talking about the first order reactions, what is happening? Just see. When we are talking about the first order reactions, right? In case of a first order reaction, now these are the reactions, which actually depend upon the concentration of the reactant. All right. These are the reactions which depend upon the concentration of the reactant. So now there are two terms, okay? One is called order. Now understand what is order. Order is a power, okay? Order is a power which tells us how the concentration, how the concentration affects, how the concentration affects the rate of the reaction. Okay, how the concentration affects the rate of the reaction. That is order. So, for example, when I talk about the first order reactions, I am going to say the rate is equals to some k constant times A raised to power 1. What is A here? A is the concentration of the reactant. Okay? A is the concentration of the reactant and R is the rate of the reaction. You understand? R is the rate of the reaction. So basically, what does that mean? You understand. When we talk about the rate of the reaction, that means the speed of the reaction. That means the speed of the reaction. And I told you that, for the first order reactions, initially, if there is a reaction from A to P, and let's suppose we have 100 molecules of A and 0 molecules of P initially at some time t, right? Here. So I hope you're understanding that at t equals to t seconds after some time. Let's suppose 10 molecules break down. So 100 minus 10. So 10 molecules of P shall be formed because one molecule of A shall give you one molecule of P, isn't it? So one molecule of A shall give you one molecule of P. I hope you're understanding. Right?
Yes, ma'am.
So 10 molecules of A, if we consume, shall give me 10 molecules of P. So how many molecules of A are we left with? We are left with 90 molecules of A, isn't it? We are left with 90 molecules of A. I hope you're understanding. And when we are left
Yes,
with
ma'am.
90 molecules of A, what exactly does that mean? You understand? When we are left with 90 molecules of A. So I told you that, every reaction is dependent upon the collisions because 99% reactions are dependent upon collision. Very few reactions which were zero order reactions, they were dependent on the external factor. Yes or no? So basically, every reaction is dependent upon the number of molecules, isn't it? Upon the number of collisions between the reactants molecule, isn't it? Between the reactants molecule. I hope you're understanding.
Yes, ma'am.
So what exactly does that mean? It means that R. It means that R rate. And what is rate? The change in the concentration of reactants, change in the concentration of reactants over time, over change in time, isn't it? Because if I say that, the reaction started at 10 a.m., ma'am, okay? I say, let's suppose the reaction started at 10 a.m. and it ended at 10:01 a.m. That means it took 1 full minute to occur. In seconds, I could say it took 60 seconds to occur, isn't it? So my point here is that, if I say rate of reaction is what? A final minus A initial upon time. Are you understanding the point? So what is A final? The reactant's concentration, which is final, minus initial. I think I have discussed this also in the previous class. So here the rate is going to be what? The rate is going to be A final minus A initial over time. Are you understanding? And that is going to be R. Yes or no? That is
Yes,
going to
ma'am.
be R. So here in this example, if I say that, 90 molecules were left, that was my initial, that was my final concentration of the reactant, minus initially the reactant molecules were 100 over time. And what was time? Time was, let's suppose, 1 minute, 60 seconds. So what is the concentration? When I talk about the concentration, I hope you're understanding that concentration means moles of solute per liter. Yes or no? So rate becomes what? Rate becomes 90 moles per liter minus 100 moles per liter. So this becomes minus 10 moles per liter over 60 seconds. So that is going to become 1 by 6 moles per liter per second. I hope you're understanding,
Yes,
isn't
ma'am.
it? And 1 by 6 moles per liter per second. But it is negative. And I told you previously as well that rate can never be a negative quantity. Since rate can never be a negative quantity, so to bring it negative, to bring it from negative to positive, we apply a negative sign here. You understand? So it becomes minus of minus and that becomes plus 1 over 6. Are you understanding? Okay.
Yes, ma'am.
So that is the concept. So when we are talking about the concentrations here, plus 1 over 6, you understand? So to make the rate positive and while expressing it in terms of the reactants, we have to put a negative sign. Because reactants with time, I hope you're understanding, they are decreasing only with time. So 100 to 0, and now they have become 90. With the time, they will also reduce to become 80 because those reactants are converting it into products. And we know that, as the reactants decrease, I hope you're understanding that with the decrease in the reactants, don't you think the collisions between those reactants decrease? Tell me. Isn't it?
Yes,
So as the reactants decrease, the collision between those reactants also decrease. And because the collisions decrease, the speed of the reaction goes on decreasing time with time. The speed of the reaction goes on decreasing with time. I hope you're understanding the concept.
yes,
So
ma'am.
just a quick recap of this. So can I say rate can also be written down as minus dA over dt? Because what is dA? A very small change in the concentration of a small change in concentration of A over small change in concentration of time, in the value of time. So dA over dt is nothing but the rate of reaction. So wherever I get to see rate, no matter what order the reaction is, I can always say it is minus dA over dt. I hope you're understanding the concept.
Yes, ma'am.
Yes or no? Now understand. Now understand. So here, what are we going to do? So for the first order reactions, what do you think I'm going to do? I'm going to say these are those reactions where the rate is directly proportional to the unit power, single power of the reactant. So K A raised to power 1. That means order means this power. So if this power is 1, I would say it is a first order reaction. That means what? That ma'am, if for a particular reaction, let's suppose you go to the lab and you say that okay, there is this reaction A to P. So what have I done, ma'am? I have taken 4 moles of A and I have put that 4 moles of A here and now I'm waiting for A to convert it into P. So maybe I will observe some color change or something. And then I can decide that okay, this reaction has taken place in, let's suppose, 10 minutes. Yes or no? So
Yes,
that's
ma'am.
my first observation. Now again I do the same experiment. Again, once I've done it, and what was my first observation? That ma'am, this reaction in occurring from A to P has now occurred in 10 minutes. You understand? Now what do I do, ma'am? Now this time I decided to take, let's suppose, some more amount of moles of A. Let's suppose I take 8 moles of A. And what will happen? Since I'm increasing the number of molecules of A, I hope you're understanding. since I'm increasing the number of molecules of A, okay, right? So these molecules of A, because they are more in amount, I hope you're understanding, these molecules will collide more. And because they will collide more, there is a chance that this reaction might take place faster. So I started to observe and I thought, and I just saw that, this reaction completed itself in 5 minutes. So what exactly happened? That as I doubled the moles, the time halved. The time reduced to half. Why did the time reduce to half? Because as the number of reactant molecules increases, their collisions increases. And when their collisions increases, what exactly happens, you tell me? That they are now going to convert more into the product and faster, at a faster rate. So now that reaction might take place in less amount of time. So that means we can understand that as and when we are increasing the concentration of A, the reactant, the reaction is happening very quickly. That means no matter what external factor it is, this reaction is not depending upon any external factor like the zero order. This reaction is dependent upon the collisions of the reactant molecules. I hope you're understanding. And now what am I going to do?
Yes.
I'm going to say, so now I'm going to derive the expression. I'm going to say rate is always called as minus dA by dt. Are you understanding? And that is equals to K A raised to the power 1. Yes or no? So A is what? A is the concentration of reactant at any time t. At any time t. So if you put in the initial concentration here, you will get the initial speed. If you put the concentration after 5 seconds, you will get the speed after 5 seconds. If you put the concentration after 10 seconds, you will get the speed after 10 seconds. I hope you're understanding. What is
Yes,
the
ma'am.
point here? Understand. The point here is that, ma'am, K times A. Now, can I say minus dA over A? Can I bring A here? And that becomes K dt. Tell me. Isn't it? Just
Yes,
tell me.
ma'am.
And if that becomes, so what am I going to get? See, tell me. 1 over A. What is 1 over A? Tell me. 1 over A is going to be ln A. Minus ln A. Or let's not do minus A. I'll carry this minus on the other side. So this becomes minus KT because integration I'm doing. Because with time, the amount of A is decreasing from A naught to AT, isn't it? Let's
Yes, ma'am.
suppose, if you remember that zero order little bit. So you will understand that, what do we have in here? We have AT is the A naught as the initial concentration. At that time, the product was zero at T equals to zero. After some time T, I hope you're understanding that, it becomes A naught minus X. So it becomes X. And what is A naught minus X? A naught minus X is AT. Right? That's what we are calling A naught minus X is. So the concentration is decreasing from A naught to AT. I hope you're understanding. The
Yes, ma'am.
concentration is decreasing from A naught to AT. So I'm going to say 1 over A. The integration of 1 over A is what? Log A. Log to the base E. And log to the base E is what, Atul? It is ln. Okay. So here it is going to become KT. And how much this decrease is taking place? This decrease is taking place in how much time? 0 to 2 t seconds. And the concentration is changing from A naught to AT. So it is going to be ln AT minus ln E naught because we are doing upper limit minus lower limit. And when we are doing the upper limit minus lower limit, that is going to become minus K T minus 0. So it is going to become ln AT over A naught is going to become, or what you can do, just make it like this, minus KT equals to ln AT minus ln A naught. Now let's bring this minus on the other side here. So it is going to become minus of ln AT minus ln A naught is going to become KT. Yes or no? And here what is happening? Here we are getting minus ln AT plus ln A naught is going to be KT. And here it is going to become what? ln A naught minus ln AT. Here is going to be KT. You understand the point?
Yes,
What
ma'am.
does that mean? What does that mean? What is the property? Log A minus log B. Log A minus log B. What is that property? That is That is log A over B. Log A minus log B, the property is what? Log A over B. I hope you're understanding.
Yes,
So
ma'am.
here if I'm getting ln AT minus ln A naught, sorry, what am I getting? I am getting ln AT minus ln A naught. Ln A naught minus ln AT, right? So if I'm getting ln A naught minus ln AT, and that is going to be KT. So don't you think it is going to become ln A naught over AT? That shall be KT. And what is ln? Ln is log to the base E, A naught over AT, and that shall be KT. Yes or no?
Yes, ma'am.
And if that is KT, what exactly does that mean? You tell me. What exactly does that mean? That would mean log A naught over A naught minus X to the base E, and that shall be KT. Because can I not write down? Because the reaction was A to P. So if I have A naught, if I have A naught here, so this would be 0. And if this is A naught, this is 0. So if this is A naught minus X, this would be X. So we were calling this A naught minus X as AT. I hope you're understanding.
Yes, ma'am.
Yes or no? I was calling this AT as A naught minus X. So I hope you're understanding that this would be log A naught upon A naught minus X. So how do I convert from base E to base 10? I'm going to multiply with 2.303 times log 10 to the base 10 A naught over A naught minus X, and that shall be KT. Understood or not? All right.
Yes, ma'am.
So this is going to be my expression. I hope you're understanding the basic concept right here. Okay.
Yes.
What am I exactly trying to tell you here? That this would be the equation. This would be the equation which would sort of, you know, solve all the possible questions of first order reactions. So you understand all radioactive decays. All radioactive decays, they come under first order. You understand?
Yes, ma'am.
So tell me one thing. Do you think that first order reactions depend upon the number of collisions
Yes, ma'am.
and zero order reactions depend upon?
External factors.
Exactly. So no matter how much moles of the reactant you increase in the zero order, would the speed of the reaction increase or will remain same?
It will remain same.
Exactly. And but if I increase the intensity of the external factor, then what do you think would happen to the zero order's speed of reactions?
Then it will increase.
Then it will increase. Do you understand? So this is the concept. So this equation is going to satisfy. So yesterday in the previous class, whatever the class we had, we did about the zero order. Today we are discussing about the first order. So my first order would be in the 2.303 log of A naught over A naught minus X equals to KT. But this equation has come when we have converted the base to 10. If I do not convert the base to 10, the equation was written down as ln A naught over AT equals to KT. Yes or no? And what is ln if I have to write down? It would mean log to the base E. A naught over AT. Why am I doing that? Because that is going to give me the graph. This blue equation is used for solving questions. Okay, solving numericals. But the same version of this, the red version of this equation, because we have actually derived this blue equation from the red equation only. But the red equation is capable of making the graph. So this equation is used for the graphical formation, the graph formation. You understand? This is important for the graph formation. Understood or not?
Yes, ma'am.
All right. So this is the concept. So when we are talking about solving numericals, okay, so this is the concept. Now you understand what exactly does that mean. If I ask you that, ma'am, this is a first order reaction. Let's suppose A to P. So initially I had, ma'am, 100 molecules at T equals to 0. So the molecules were very high in number. So there were large number of collisions. I hope you're understanding. Yes or no? There were large number of collisions. Now, because there were large number of collisions, do you understand that, as the time passes by, it becomes 90 molecules? As the time passes by even more, it becomes 80 molecules. As the time passes by even more, it becomes 70 molecules. It becomes 60 molecules and so on. There must have been a time where the molecules would become just two because the 98 would be then converted into products. Do you think the intensity of collisions when there were only two reactants left? Do you think that the intensity of the collisions would be very high at two reactants left only? Do you think the intensity of collision will be very high when only two reactant molecules are left?
No, ma'am.
No. With regards to 100 reactants, with regards to 90 reactants, only two reactants or only one reactant is left. Do you understand that the vibrations would be more or less? The vibrations would keep on decreasing.
Yes.
That means if 100 molecules are there, there are more collisions. It might take few seconds, to convert it into product. But at 80 molecules, it might take little more time. At 60 remaining reactants, it might take even more time and so on. So first order reactions basically, gradually their speed goes on decreasing and they sort of, take a lot of time. They take a lot of time. Are you understanding? So when they take a lot of time, what exactly does that mean, Atul? Effectively, the full lifetime of first order reactions, the full lifetime of first order reactions, okay, is infinite. Is infinite. I hope you're understanding. The full
Yes, ma'am.
lifetime of a first order reaction is infinite. That means if you expect that only, okay, at some point in time, the reactants would be zero. You understand? At some point in time, the reactants would be zero. So that to become zero, the reactants to become zero would take a lot of time. I hope you're understanding the concept.
Yes, ma'am.
And because they're taking a lot of time, so effectively for us, it is going to be an infinite amount of time. Any doubts up till now, just tell me that.
No,
Okay,
ma'am. Clear, ma'am.
right? Now understand. Now, similarly, here, what are we doing? Now, let's discuss certain important points about it. So, we would have the half lifetime. Half lifetime, what are we trying to calculate? The time in which the reaction is completed into half. If you have taken 100 reactant molecules, so what is the half? That how much time it would be required to convert 50 molecules into product and 50 reactant molecules are still left, isn't it? So 50 are left because 50 have been converted into products. Are you understanding my point?
Yes, ma'am.
So we have this. So now what is the equation? So we have KT equals to 2.303 log of A naught over A naught minus X. Now you tell me. So we are finding KT half equals to 2.303 log of. So let's suppose A naught is the initial concentration. So 50% is left and 50% is consumed. You understand? So when 50% is consumed, what is happening? When 50% is consumed, what is happening? You tell me. So we would be left with A naught by 2 would be left. A naught we took. A naught by 2 got consumed in some T half time. So we are left with A naught minus A naught by 2. Are you understanding? So we took
Yes,
A
ma'am.
naught. I hope you're understanding. A naught by 2 got consumed. And then we are left with A naught minus A naught by 2. That would be 2A naught minus A naught by 2, which is A naught. So here, what are we substituting? A naught we took in 80. This was 80. This was 80. But 80 is basically how much we are left with. Okay, how much we are left with. So we are left with A naught by 2. So we have KT half is going to be 2.303 log of A naught cancels A naught and this becomes log 2. Do you understand?
Yes, ma'am.
So 2.303 into log 2 is 0.3010 shall be k t half. So t half here shall be 0.6931. If you multiply 2.303 into 0.3010, that comes out to be 0.6931 divided by k. Understood or not? And that
Yes,
is
ma'am.
t half. That is t half. What exactly does that mean? So for the first order reaction, my main equation is this. This is my main equation. And t half is going to be my 0.6931 over k. Are you understanding the concept?
Yes, ma'am.
All right. Now, just understand. So we have this half lifetime. Now, just have a look. So did I teach you that, ln A naught by AT was KT minus KT was KT? So sorry. This was the equation I told you we are going to use for graphs here. When I told you about the red equation and the blue equation. This one.
Yes, ma'am.
ln means log to the base E. And log to the base 10 is something that we work on. We solve log to the base 10. Here, you understand. When we have this equation, right? What exactly do you mean by the term log? Can I say ln is nothing but log A naught over AT to the base E is KT?
Yes, ma'am.
I hope you understand the meaning of log. What is log? When I say log 10 to the base 10, what is the answer, Atul? See, it means like this 10 raised to power what? So let's suppose some answer x. Okay, I do not know what. So I would say 10 raised to the answer x should give back me 10. Just remember this circle. 10 raised to power x should give me back 10. So can I write it down this way? That ma'am, it would be what? Tell me. Don't you think it should be x equals to 1? Yes
Yes,
or no?
ma'am.
What is the point here? The point here is that ma'am, if I have 10 raised to power x is 10 raised to power 1, yes or no? So if I say log 100 to the base 10, that would be something. So what should be your answer? Ma'am, 10 raised to power what should give me 100? So let's suppose ma'am x. So 10 raised to power x, that means that should be 100. Are you understanding this circle? This is the base. So my question to you is with log that 10 raised to the power what? This x should give me back 100. That's how we have to get the answer. So what should be the value of x here, you tell me?
10, ma'am. Oh, sorry, 2. Ma'am.
So x is going to be 2. When I say log, 8 to the base 2, what is the answer?
3,
2
ma'am.
raised to power exactly to give me 8. So my point here is that if I have this expression right here, I hope you're understanding that e raised to the power kt shall give me this, isn't it?
Yes, ma'am.
So what would that be? What would that be? Don't you think it should be e raised to the power kt should be a naught over kt? Because this shall be left here and the base here is e. And what is e, Atul? E's value is 2.7. E is called Napier's constant. All right. So normally to understand it approximately, I explain it with 3, but the exact value of E is 2.7. So I hope you're understanding that, A naught over 80 is some number. So I would read log in the same manner. I would say E is the base. So E raised to the power KT should give me this. Now if I reverse it, what does it make? It makes AT over A naught. So that would be 1 over E raised to power KT. And what is 1? 1 could be written down as E raised to power 0 because anything raised to power 0 is 1 over E raised to power KT. Are you understanding?
Yes, ma'am.
What exactly does that mean? You tell me. So, and now when the bases are in division, when the bases are in division, what exactly does that mean? It would be e raised to power minus kt. You understand? So can I
Yes,
say a no, at by a naught is equals to e raised to power minus kt, and at thereby would be a naught into e की power minus kt. That is my general term of whatever concentration is left at any time t. So what is at? At is the concentration of the reactant at any time t. Understood or not?
yes, ma'am.
Yes or
Understood.
no? You understand?
Yes, ma'am.
So that is the concept. So this equation, this graph, ये जो मैंने लंबोर्गिनी बनाई है यहाँ पे, है ना, ये हमारा ग्राफ बनाएगा. Do you understand? ठीक है? Understood?
Yes, ma'am.
Okay, great. Now understand. So up till now, what we have learned that, ma'am, if R equals to K, some concentration A raised to power 1, this would be called as the first, this shall be called as the first order reactions. Secondly, secondly, what do we have in here? That if I double the concentration, let's suppose this time rather than adding A moles, I would add 2 A moles. So initially, let's suppose the rate was R1, so now the rate is R2 raised to power 1. If I divide it, I hope you're understanding, R1 over R2 shall be K cancels K, it shall be 1 over 2. That means 2 times R1 is going to be R2. You understand? 2
Yes,
times
ma'am.
R1 is going to be R2. I hope you're understanding.
Yes, ma'am.
Okay. Similarly, if I make the concentration 5 times, so let's suppose if I say R1 is equals to K into A raised to power 1. That means when you have taken 1 mole of A, so 1 mole or 2 moles or whatever the initial concentration of A that you've taken, the rate is R1. That means the speed is R1. Now you have what? You have done what? You have increased the concentration 4 times. Now you have added 4 times the number of moles of A. So what do you have? You have R2 over R1. If I divide it, what will I get? I will get K into 4A raised to power 1 over K into A raised to power 1. So K cancels K, A cancels A. R2 by R1 shall be 4. So R2 shall be 4 times R1. So in first order reactions, if you increase the concentration, if you double it, the rate shall also be doubled. If you increase the concentration, if you make the concentration 3 times, the rate shall also be 3 times. If you make the concentration 5 times, the rate shall also be 5 times, and so on. You understand?
Yes, ma'am.
All right. So this is the concentration. Are you understanding? This is first thing. The equation that you will be using to solve the first order will be Kt equals to 2.303 log of A naught over A naught minus x. The T half lifetime that you have calculated here is 0.6931 over K. And in this reaction, I hope you're understanding that T half, it doesn't matter, whether you initially you take 100 molecules or whether you take 1000 molecules. If 100 molecules becoming 50, if they take 10 minutes, so 1000 molecules becoming 50 shall also take 10 minutes. You understand? Becoming
Yes, ma'am.
500, sorry. 10,000 molecules becoming 5,000 shall also take 10 minutes. Are you understanding? So what
Yes,
exactly
ma'am.
does that mean? That, ma'am, because why is that happening? Because as you're increasing the number of molecules, as you're increasing the number of molecules, okay, what is happening? When you're increasing the number of molecules, the collisions are also increasing. And when the collisions are also increasing, that means that this reaction is taking occurring at a half faster rate. the 10,000 one, with respect to the one where we had only 100 molecules initially. Are you understanding what I'm trying to explain you?
Yes, ma'am.
Sure. So what my point of explanation here is that for the first order reactions, you do not have to worry about the half time. Half time does not depend upon the initial concentration. Why so? Because the moment you increase the concentration, the speed of the occurrence of the reaction also doubles itself. Are you understanding my point?
Yes, ma'am.
So this is the concept. You understand? So here, if I draw the graph of R naught, sorry, if I draw the graph of T half versus initial concentration. So no matter whether you increase the initial concentration, every time the initial concentration is increasing, the half-life time is still the same. You understand? Because at a faster. So write it down. This is an important understanding that no matter how high the initial concentration is, no matter how high the initial concentration of the reaction is. Okay? No matter how high the initial concentration of the reaction is, the half-life time remains the same. The half-life time remains the same because at higher concentration, the reaction occurs at faster rate. Yes or no? So here you
Yes, ma'am.
understand in 10 minutes, 5,000 molecules have to be consumed. And when the initial reactants were 100, in the same 10 minutes, 50 molecules have to be consumed. So don't you think that, here they have the leverage of being slowly moving, and still in 10 minutes they have to cover just 50 molecules. So per minute, they can cover up 5 molecules. But here, when they have to consume 5,000 molecules in 10 minutes, so per second, they have to cover up 500 reacted molecules. So here, the collisions are more, speed of reaction is more. So as to keep the half-life time same. And that's what my formula is also telling me, that there is no, what do you call? Here, there is no interference of the initial concentration. Nowhere in the formula, you're getting A naught. Next, you see. So for example, if I say R equals to K A, and I also learned the formula that AT equals to A naught e raised to power minus KT, isn't it? Now you tell
Yes.
me, what did I explain you? What is A? What is A? A is concentration.
Concentration at any time t.
Concentration of reactant at any time t. Yes or no?
Yes, ma'am.
So when I say R equals to K and A, instead of A, I'm going to write down A e ki power minus KT. Can I do that? Because AT is also what? AT is also the concentration at any time t. Yes or no?
Yes, ma'am.
So when I say R equals to K A naught e ki power minus ET, e ki power minus KT, so you tell me what is happening. As the time is increasing, at time t equals to 0, R equals to what? K A naught e raised to power minus K times 0. Anything raised to power 0 is 1. So initial rate is K A times A naught. Then at time t equals to 1, R becomes K A naught e raised to power minus K. For some time, just remove K. Let's suppose K is 1. Let's suppose for some time. So don't you think it is going to become minus 1? E
Yes, ma'am.
raised to power minus 1 basically means K A naught by E. E is nothing but 2.7, rounded off to 3. So new rate is basically one third. Just after 1 second, the new rate shall become one third approximately. My point here is that, here you have divided with 3. Next, at t equals to 2 seconds, just put in the value K A naught e raised to power minus 2 is R. So R shall be K A naught over E square. But the value of E is approximately 2.7, is exactly 2.7 and approximately 3. So if I look at the value approximately, it becomes Ka naught by 9. Do you understand how drastically the rate is decreasing?
Yes, ma'am.
What am I trying to tell you here? I am trying to tell you here is that when you say R equals to Ka, and when you say At is equals to A naught e raised to power minus Kt, and you substitute this value here, because this is also concentration at any time t. So you will say R equals to K A naught e raised to power minus Kt. So the graph of rate versus time, with the time, what happens to the rate of the reaction? It decreases drastically. It decreases when E is there, it decreases exponentially. Do you understand that just after 1 second it became one third? It became R 1/9. So it is decreasing 0 seconds, 1 seconds, 2 seconds, 3 seconds. So just at the second, it was, if this was the rate, one third would be something here and 1/9. So the graph would grow something like this. And here also, if I draw the graph of AT is what? Concentration of reactant versus time. So as the time passes by, initially the reaction, the concentration of the reactant, that consumes very quickly. The reactant gets consumed very, very quickly. You understand my point? So this graph
Yes, ma'am.
decreases like this again. Because this graph I'm drawing according to this equation, that this is telling me that what would be the leftover concentration. What would be the leftover concentration after time t, isn't it? I hope you're understanding.
Yes, ma'am.
Similarly, if I tell you this, so understand one thing. I hope you're understanding, for this reaction A to P, I told you my initial reactant was A naught. So product was 0. After some time, A naught minus X, because X is getting consumed, so X amount of product is being formed. So I hope
Yes,
you're
ma'am.
understanding that A naught minus X is nothing but AT, that is AT.
Yes,
And I
ma'am.
know that AT is nothing but A naught e raised to power minus KT. But AT is also A naught minus X. So can I say, instead of AT, can I say A naught minus X would be A naught e raised to power minus KT?
Yes, ma'am.
So it would be what? Just tell me. It would be what? It would be A naught, bring this here, minus A naught e raised to power minus KT shall be X. So if I bring down A here, it would be 1 minus e raised to power minus KT shall be X. Are you understanding?
Yes, ma'am.
What is this? What is this? This is X. X is what? The amount of product form. Are you understanding? Okay. X is
Okay.
what? X is representing the amount of product form. Just have a look. Are you understanding?
Yes, ma'am.
Now have a look. Do you realize that I explained you e raised to power minus kt? What happens to e raised to power minus kt? T is time. When t was 0 seconds, e raised to power 0 it became. E raised to power 0 is 0. E raised to power 0 is 1. E raised to power 0 is 1.
One. Yes, yes.
1 minus 1? 1 minus 1
Sir.
is 0. X is 0. That means at t equals to 0, the product was 0. That's what this equation is showing me.
Yes,
Now,
ma'am.
as the time passed by, so let's suppose 1 seconds. So when you put t as 1, it means e raised to power minus 1, approximately. E raised to power minus 1 would mean 1 over e. E raised to power minus 1 would mean 1 over E, isn't it?
Yes, ma'am.
And 1 over E is what? 1 over 3.
1
So 1 minus 1 over 3 would give you x. So 1 over 3 is what? You tell me. 1 over 3 is 0.33. So approximately you get 0.67. You understand?
Yes, ma'am.
Then what happens? You tell me. As t passes by, t is 2. It becomes 1 over 3 square. What is 1 over 3 square? 1 over 9. And 1 over 9, 1 minus 1 over 9. 1 over 9 is 0.11 if you divide. So 1 minus 0.11. What am I trying to explain you? That with time, e raised to power minus kt is going to decrease, isn't it?
Yes, ma'am.
So if you subtract 1 minus 0.33, you get 0.67. When you subtract 1 minus 0.11, what do you get? What do you get? You get 0.99, isn't it?
Yes, ma'am.
What am I trying to tell you? That as the time passes by, e raised to power minus kt it goes on decreasing, and 1 minus which is getting decreased, 1 minus smaller number will give me a bigger answer. So
Yes,
with
ma'am.
time x is increasing, isn't it?
Yes, ma'am.
Did you understand this explanation, right? So
Understood, ma'am.
when this happened, how would the graph of the concentration of products, sorry. So how would the graph of the concentration of products versus time? So x versus time. What is x here for me? X, I'm representing the concentration of products versus time. So don't you think it is a x is what? A naught into 1 minus e raised to power minus kt. So with time, that is increasing. You understand?
Yes, ma'am.
And initially it increases immensely, and then gradually the slope lowers down. Because because the collisions of the reactions are decreasing. So the products are also not being formed at a quick rate. Understood? So this is going to be x.
Yes.
Then what do we have in here? So this is x. X is the amount of product. So three equations we have for here. So if you have r equals to r a naught k a naught e raised to power minus kt. So the rate decreases exponentially. And that is the difference. For the first order, every graph is either like this, like this, like this. But for zero order, all the graphs are straight line like this, this, this. So zero order, everything has got something to do with the straight line. For the first order, everything has got something to do with the exponential curve, which could be either increasing like this or decreasing like this. Okay, right?
Okay, ma'am.
So this is the basic thing. So now when you find certain reactions, okay, so this is going to be my first order reactions. So let's suppose you have certain questions on that. So let's suppose the first question that you get is this. Let's suppose the question says, calculate the amount of time required to complete 90% of a reaction if the rate constant of the reaction is if the rate constant of the reaction is 62.7 into 10 raised to the power minus 3 10 raised to the power 3 seconds inverse. That's the rate constant. Okay, 10 raised to the minus 3 you said. So rate constant, so look at the value of the rate constant. What is rate constant? Rate constant is the constant K. And I do not know whether it is a first order reaction or it is a second order reaction. I do not know that. What would I do? I would say R equals to K A raised to power 1. Let's check that out. What is R? R is the rate of reaction. Rate of reaction is what? The unit of rate of reaction is fixed unit. It is moles per liter per second.
Second.
And that would be equals to K. And A would be what? A would be moles per liter. Yes or no?
Yes, ma'am.
So K here would be what? K here would be moles per liter per second divided by moles per liter. So do you understand that moles per liter cancels out each other? So K
Yes, ma'am.
here shall be second inverse. K here shall be second inverse. Are you understanding?
Yes, ma'am.
So just have a look at the unit of K here. Isn't it seconds inverse?
Yes,
So
ma'am.
this unit of K itself tells me that it is going to be a first order reaction. All right. It could be simply minute inverse. It could be simply hour inverse. It could be anything. You understand my point?
Yes, ma'am.
So it says calculate the amount of time required to complete 90% of the reaction. So what am I going to say? I do not know how much was the initial reactant. So I would say, let's suppose I had 100 reactants initially. You understand? I had 100 molecules of reactants initially. All right. Is it 11? Okay. All right. So then what we are doing, Atul? We are saying that calculate the amount of time required to complete 90% of the reaction. So I would say KT equals to 2.303 log of A naught over 80. 80 is what? How much amount is left? So I hope you're understanding that KT shall be 2.303 log of. How much is A naught? How much we have taken initially? I do not know. Let's let it be 100. Over how much are we left with? The reaction has completed itself by 90%. Are you understanding? And when the
Yes.
reaction is completing itself by 90%, that means we are left with just 10 molecules of reactants. Okay? And K is given to me 62.7 into 10 raised to power minus 3. And the question is asking you how much amount of time would be required to complete 90% of the reaction. So time we have to calculate. Yes. So it would be T equals to 2.303 log of 10. And here the base is 10. So log 10 to the base 10. What should be the answer? You tell me.
1, ma'am.
1. Good job. And divided by 62.7 into 10 raised to power minus 3. Understood or not? Just tell.
Yes, ma'am.
Okay.
Understood.
So this is how we get the answer. And now you just solve this to get the time. So this would be something about like this. It would be something around like this. Like 2.303 divided by 62.7 into 10 raised to power 3. Yes or no?
Yes, ma'am.
Okay. So this is the answer. So these many seconds would be required for the complete conversion of the reaction by 90%. So that's how we apply this particular formula. Understood or no?
Yes,
Okay.
ma'am.
So we'll be doing some more questions tomorrow. I'll drop in the time. I know the timings now.